Hello, I'm Habib and I'm going to present our work SNR, Network-Aware Geo-Distributed Stream Analytics. This is a joint work with Shafi and Jamal. Applications running on top of IoT devices or user clicks in social networks generate a massive amount of streaming data from geographically distributed locations. Organization needs to analyze and mine this amount of data in order to get insights and valuable intelligence such as trend detection on social networks. These applications have stringent requirements such as low latency and high bandwidth. It's not practical anymore to process this amount of data in a single location. Therefore, the idea of geo-distributed processing system is a popular choice for processing this amount of data. In this case, we have several data centers that are geographically distributed, and the idea here is to push the computation close to the users. This can help us to preserve the privacy of data and reduce the cost by reducing the overhead of data transmission over WAN links. Here, you can see an example of geo-distributed processing system. There is a global manager and 5 data centers that they are connected through WAN links to each other. Each link has diverse properties such as delay, latency, and cost. And there are some applications and frameworks that can process the incoming data from the users on top of these systems, such as Apache Spark, Apache Storm, and Apache Flink. Even though these applications could process massive amount of data, their application on the WAN scenario comes with several constraints and fundamental challenges such as resource management in a geo-distributed setting. The motivation for our goal is to answer the following question. How we can prioritize network metrics in order to efficiently run a task on a geo-distributed cluster network, and what is the trade-off among different network parameters in placing workers in a multi-cloud environment. So we want to place the workers in such network according to user preference, and we want to minimize the delay and cost while obeying the bandwidth constraints. To model the problem, first we model the delay. We assume the internode delay in a geographically distributed cluster. Suppose that we have selected a subset of nodes from network graph G, and the goal here is to minimize the sum of delay. So we use TXY as the link delay in millisecond between node X and node Y, and here N is the number of chosen worker nodes in a cluster, and G prime is a subgraph of G. Similar to delay, we model the cost as following. We assume the data transmission cost from worker node X to Y through a link between them, and in the subset of selected nodes, the goal is to minimize the cost among all the chosen nodes. So CXY is the cost of steering 1 GB of traffic from node X to node Y. Also, we consider the bandwidth. Let be the available bandwidth of the link from node X to node Y. The goal here is to maximize the minimum available bandwidth among the chosen nodes in graph G prime. For example, consider 4 nodes A, B, C, D here, and there are different bandwidth among the links between these nodes. For example, the bandwidth between A and B is 10 Mbps, B and C is 7 megabit per second, and between C and D is 8 megabit per second. If we want to send traffic from A to D, the maximum amount of traffic that we can send based on this available bandwidth is 7 megabit per second. So we want to obey these constraints in selecting worker nodes in our solution. So the proposed mechanism, we called it SNR, which is a simple additive weighting-based method to transform our problem to a single objective one. Since we have multi-criteria in selecting worker nodes, we use SO method to transfer our problem to a single objective one. Our SNR has two phases, first node selection and remaining node selection phase. In the first node selection phase, we rank all the nodes in the network graph and we select the node with the highest rank as the location of first node. And in the remaining node selection phase, we rank all the nodes connected to the current selected nodes and select the node with the highest rank as the remaining node. So we repeat this procedure until the desired number of worker nodes has been selected. To select the first node, first we need to normalize all the links values such as latency, cost, and bandwidth. Consider that we have a link between node X and node Y. So in order to normalize the value of bandwidth, we will find the average value of bandwidth that are connected to each node. For example, here we have one link, but if we have multiple links connected to X and Y, we will take the average value of bandwidth and we divide this value over the maximum value, since the maximum is better. We do the same mechanism for delay and cost, while in the case of delay and cost, the minimum value of delay and cost is better for us, and we divide the minimum value over the average value in order to normalize the value. After normalization, we rank all the nodes, and we call it R node as a rank of the node. So since we have we consider three different parameters, bandwidth, latency, and cost, we use a coefficient for each one. So in this equation, n is the number of neighbor nodes of a node, and Wk is the priority weight of each attribute. We use W1 for bandwidth, W2 for latency, and W3 for cost. The sum of these values should be 1. After finding the rank of each node, we select the node with the highest rank as the location of first node. Now we need to select a subset of nodes to add to the current selected nodes. We will use the neighbor of current nodes to select further nodes. To do so, we normalize the parameters. In this case, we don't need to find the average since we are interested in checking the neighbors of the current node. And we do the normalization for bandwidth and cost and select the node with the highest rank as the next node. We repeat this procedure until the desired number of worker nodes or locations have been selected. Now, I will show an example of our algorithm to see and explain how SNR selects the worker nodes in a graph. Here is an example graph of 6 nodes, and there are some links between the nodes, and each link has 3 different properties: latency in millisecond, bandwidth in megabit per second, and cost in US dollar as the cost of transferring 1 gigabyte of data over that link. To run our algorithm, first we need to find the rank of each node. The orange values behind each node in this graph shows the rank of each node. By checking the rank values among all the nodes in this graph, we find that node 3 has the highest rank, therefore we will place the first worker in node 3. Now we need to suppose that we want to add 3 nodes and we want to select 3 nodes for our cluster. After selecting node 3, we check the neighbors of node 3 to add further nodes. So node 1, node 2, node 4, and node 5 are the neighbors of node 3. So we need to find the rank of each node. After doing the calculation, we find that among the neighbors of node 3, node 4 has the highest rank. Therefore, we add this node as the next node to our current cluster. So we repeat the same procedure, and after checking the rank of nodes neighbors of node 4, we find that node 5 has the highest rank, and we select node 5 as the next node. So at the end, node 3, 4, and 5 are selected as the worker nodes for our cluster. Now we evaluate SNR on different networks, and we want to answer the following questions. How does SNR select nodes on the networks of Topology Zoo, and what is the performance improvement of SNR on the current stream processing systems? First, we show the results on the networks of Topology Zoo, and we run SNR on all the networks of Topology Zoo. In this graph, the x-axis shows the number of workers that we place in a network, and y-axis shows the average delay among the chosen nodes in the graph. So here we have the results for SNR and default, and in the default case, the nodes are selected in an order fashion. And we find that the average delay among the nodes are 1.44 times less than default approach in SNR. We also measure the hops among the worker nodes in SNR, and we find that SNR has 1.41 times less hops compared to the default approach. Furthermore, we create 3 custom graphs, and we want to measure the performance of SNR on the custom graphs running on real systems, real stream processing systems. These graphs, we name them small, medium, and large. In the case of small, we have 20 nodes with 35 links. The bandwidth among the nodes vary in the range of 7 to 14 megabit per second. The delay varies in the range of 1 and 25 milliseconds, and the cost is in the range of 2 to 25 cents. In the case of medium, we have 30 nodes with 65 links, and the only difference compared to the small is that the delay varies in the range of 26 to 75 milliseconds. And in the case of large network, we have 50 nodes with 140 links, and the delay varies in the range of 76 to 125 milliseconds. Here, we use the same values for bandwidth and cost. To evaluate SNR on real systems, we use the Yahoo streaming benchmark. This benchmark emulates an advertisement analytics pipeline, and it measures the performance of distributed stream processing systems. The benchmark generates data as the input to the system and measures the performance of the system. Our testbed contains 11 VMs with 16 CPU cores each and 8 GB of memory. All the systems running on Debian. We dedicate 8 VMs for the worker nodes, and each worker node has 6 task slots to run the job. We use 1 VM for the master node, 1 VM for Kafka, and 1 VM for Redis. And we also run Zookeeper on Kafka. So since we need to generate data, we use Kafka and Redis for data generation. And in the query of the benchmark, the Kafka is the source of the data and Redis is the sink for data. We use 3 systems to measure the performance of SNR: Apache Storm, Apache Spark, and Apache Flink. Each of these systems has some parameters to tune, namely parallelism, record acknowledgement, and batch interval all are the most famous ones. So we use the parallelism of 6 in each system. We disable record acknowledgement in the case of Apache Storm by setting this value to 0, and Apache Spark has a parameter which is called batch interval, and we set the batch interval to 10 seconds. Here we report the execution latency, and to be more precise, the 99 percentile execution latency of query on the custom graphs, and you can check the paper for more results such as average link delays in custom graphs and trade-off among different network-related parameters. We first show the performance of SNR on small graphs, and we find that in the case of Spark, our system improves 1.5 to 2.9 times compared to default approach in the case of Spark. Here in these graphs, the x-axis shows the input data rate as the load to the systems, and the y-axis shows the 99th percentile execution latency. In the case of Apache Storm, we find that SNR improves 1.1 to 2.5 times compared to default approach, and in the case of Apache Flink, it improves 1.1 to 1.4 times compared to default approach. Now we repeat the same experiments on medium topology, and in the case of Spark, we find that SNR improves 2.2 up to 7.2 times compared to default approach. In the case of Apache Storm, it improves 1.2 to 3.4 times, and in the case of Apache Flink, it improves 1.4 to 3.3 times the execution latency of the system compared to default approach. To conclude our work, in this paper we proposed a simple additive weighting-based methods for worker node placement in a geo-distributed cluster. The users of our system can prioritize the task execution according to network-relevant parameters, and our solution finds the trade-off among different network-related parameters such as the available bandwidth, latency, and cost in placing the workers. In the future, we want to extend our work to include physical resource information such as CPU usage and the available memory in placing the workers, and we want to use the concept of SDN to have dynamic monitoring of the network usage such as the available bandwidth and the latency among the nodes. Thank you for your attention.